All right, welcome to The Explainer. Today, we're going to crack open one of chemistry's biggest secrets. It's a formula that lets us figure out the energy of almost any chemical reaction, all without ever having to go near a lab. Let's see how it's done.
So first, let's start with a problem. Think about it. A lot of chemical reactions are just messy, or they're flat out dangerous to handle. Imagine you're trying to measure the energy from toxic stuff forming way up in the atmosphere. It's not just hard, it's pretty much impossible to do safely.
And that leaves us with a huge question. If you can't actually measure the energy of these reactions, how can you ever really understand them? How are you supposed to engineer cleaner fuels or better industrial processes if you don't know the numbers? How do we get that data?
Okay, let's get specific. Take acid rain. You've got sulfur dioxide getting pumped out of power plants. It mixes with oxygen in the air and makes sulfur trioxide. That's a huge step in forming acid rain. But trying to bottle that reaction up in a lab to measure it, it'd be a total toxic nightmare.
But this is where it gets really cool. Chemistry has this absolutely brilliant workaround. It's like a secret shortcut that lets you calculate the exact answer you need with just a pen, some paper, and a cheat sheet of values. No lab coats, no hazardous waste, just pure chemical logic.
And the hero of our story is this thing called the standard enthalpy of formation. Now, don't let the name scare you. Enthalpy is just a chemist's fancy word for the total heat energy of something, and the idea is really simple. It's just the amount of energy that changes when you build 1 mole, think of it like a chemist's version of a dozen, of a compound from its most basic raw elements.
Honestly, the best way to think about it is like this. Every single chemical compound has a universal energy price tag. That tag tells you exactly how much energy it costs or how much you get back when you build it from the ground up. And once you know the price tags for everything you start with and everything you end up with, the rest is just simple math.
Of course, for these price tags to actually be universal, everyone has to be working from the same starting point, right? So in chemistry, we have something called the standard state. It's just a set of baseline conditions, 25 degrees Celsius, basically room temperature, and about normal atmospheric pressure. It keeps everyone on the same page.
So what does this standard state actually look like? Well, for oxygen, it's a gas. For sodium, it's a solid. And for a few weirdos like mercury and bromine, they're actually liquids at room temperature. These are our fundamental baseline building blocks.
So if all the compounds have these energy price tags, what's the price for the raw ingredients themselves? For the pure elements in their standard state? Well, the answer is the most important rule of this entire game, and it's beautifully, elegantly simple. The cost is exactly this.
We call it the elemental zero rule. And it says that the standard enthalpy of formation, our price tag, for any pure element in its most stable form is defined as 0. Period. Why? Well, because they're the starting line. You can't build an element from anything simpler. It's our ground zero, so it costs nothing to start there.
Okay, enough theory. Let's put this incredible tool to work.
We're going to calculate the energy that gets released when you burn 1 mole of methane. That's the main stuff in natural gas. It's a reaction that happens every single day in furnaces and stoves all over the world. So the thought process here follows this really logical 2-step path. First, we imagine taking our starting materials, our reactants, and we calculate the energy it would take to break them all the way down into their pure elements. Then, we calculate the energy we get back when we reassemble those same elements into our final products. The net change is just the difference between those 2 steps. And all that logic, it gets boiled down into this one elegant, powerful equation. The total energy change of a reaction is just the sum of the price tags of all the products minus the sum of the price tags of all the reactants. It's literally just the energy of what you made minus the energy of what you started with. Simple as that. Okay, let's plug in the numbers from a standard table. On the reactant side, we have methane. Its price tag is negative 74.4. And then we have oxygen. But wait, it's an element in its standard state, so its price tag is 0. See how that works? Then on the product side, we make carbon dioxide, and we also make 2 moles of water.
So we have to be sure to multiply water's price tag by 2 to get the correct total. So we add up the products, we subtract the reactants, and we get our final answer, negative 890.7 kilojoules. And that negative sign is key. It tells us the reaction releases energy into the surroundings. It's exothermic, which is exactly what you'd hope for when you're burning a fuel.
So this is way more than just a classroom problem. We can use this exact same method to answer real, practical engineering questions. Like, for instance, which of two different fuels is actually better? Which one packs a bigger punch?
So let's set up a little showdown. In one corner, you've got methanol, which you'll find in some high-performance race cars. And in the other corner, you've got octane, which is pretty much what gasoline is made of. We can use our formula to figure out which one gives more bang for its buck.
And after you run the numbers for both and, importantly, adjust for their weight, wow, the results are pretty stark. For every gram you burn, methanol gives you about 22.7 kilojoules. But octane? Octane gives you a massive 47.9 kilojoules per gram.
The winner is clear. For the same amount of weight, octane packs more than double the energy of methanol. And that's exactly why it's the go-to fuel for our cars. It means you can go more than twice as far on a tank of gas. And we figured that out just with our chemical price tags. No experiment needed.
And this right here is the biggest takeaway. Using the standard enthalpy of formation, we can accurately predict the energy for a huge number of reactions, from what's happening in your car engine to what's happening in the sky, all from the safety of a desk. It's basically a predictive superpower.
And that leaves us with one last pretty mind-blowing thought. This tool isn't just about understanding the reactions we already have. It's about designing the ones we need for the future. So the real question becomes, now that we have this power to calculate and predict, what new, cleaner, more efficient fuels can we start to engineer on paper today to go and build a better world for tomorrow?